Hi everyone, and welcome to course number 3, E-Motor Production. My name is Moritz Stöckler and I am Research Associate at the Chair of Production Engineering of E-Mobility Components, PEM, at the RWTH Aachen University in Germany. I previously worked in the engineering department at Mercedes-Benz for several years. And yeah, so much for me in person. Let's get started. This is module number 2, hairpin stator production. We start with some basics and product features of the hairpin stators. After that, we go step by step through the manufacturing process of hairpin stators. This will take some time, so that we only take a short look on the current market and patent situation, and some product and process restrictions after that. Let's get into it. This presentation shall explain you the basics of Stator technology in hairpin design. This presentation shall you describe characteristic product properties and the process chains and of different hairpin stators. And this presentation shall illustrate the interdependencies in the production process for hairpin stators. First point, basics and product features of hairpin stators. Yeah, if we take a look on the process chain of electric motor production, the rotor and the stator production are the most complex parts in terms of manufacturing. In this module, we will deep dive into the stator production. Other than the rotor, which we will learn about in module 3, the stator design is mainly independent of the motor topology. So either if we use an induction machine, a permanent magnet synchronous motor, or an externally excited synchronous motor, the stator will look pretty much the same. The hairpin stator technology is comparatively new for electric motors. Previously, winding processes with round wire are established. We can divide between direct winding processes like the needle and the flyer winding and indirect winding processes like the flyer wrapping and feeding, which also use round wire, and the hairpin technology, which uses flat wire. The advantage of this technology and the use of flat wire is that we bring more copper at the same space into the stator, which increase our electric slot fill factor compared to all windings using round wire. We also have a deterministic process control, which benefits production of many units with consistent quality, which is favored in the automotive industry. But again, it is a relatively new technology that comes with new challenges for the production and the industrialization process. Let's take a closer look on the hairpin technology profile. Uh, the flat or solid conductors are formed into pins that created a plug-in coil, which are inserted then into the stator slots. Advantages are, like I said, a higher slot fill factor, which results in higher current strength and a stronger magnetic field. Disadvantages are the high investment costs of a production line and yeah, a low variant flexibility. We have many individual process steps with individual special machines, and yeah, we will learn much about this today in this lesson. And yeah, especially the pin forming process and the welding process are critical. But what is the motivation to switch to this technology, even if the production process is more complex? Now, first of all, we have economic efficiency. With a high automation capability of the production process, um, which reduce costs. Um, yeah, and we already talked about that we have a deterministic assembly and welding process, which is favored in the automotive industry. At the same time, we gain high torque motors with at the same time high efficiency due to the higher current and stronger magnetic field. And when we look to the future, we have still high potential if we solve the teething troubles in the technological maturity. On this slide, we compare the different plug-in coil concepts. With the I-pin technology, the pins will not be bent before they are inserted into the stator slot. The downside is that we have twice the number of welds because we need to contact the pins on both sides of the stator with each other. And yeah, with the U-pin technology, we solve this problem. We shape the pins into a U form, which looks like a hairpin due to a 2D and 3D bending process. Yeah, with the advantage of a reduced number of welding spots because we only have to contact the pins on one side. With the continuous hairpin winding, we do not cut the wire into single pins, but we shape long continuous winding mats. Today we see this only in luxury vehicles or in hybrid applications, and yeah, we will not focus this technology in this presentation today. This slide shows why we mainly use copper as conductor material. In terms of electrical conductivity, copper is only the number 2 behind silver. But when we look at the costs per kilogram, copper is only a tenth of silver. Yeah, which makes the choice pretty easy. Um, but we also see some interest in aluminium as a conductor material today, due to its even lower cost than copper. And yeah, graphene is a future material out of carbon and not usable today as a conductor. We also have good thermal conductivity with copper and a high melting point, which allows us to supply it with high current strength. Let's take a short look on the further processing of the raw copper into winding wires. We can pull the copper through smaller die holes from drawing stage to drawing stage to bring it into the wire shape. Or we feed the copper wires through a pair of rollers to give the wire the right profile. But we can't use raw copper wires in the stator. We have to insulate them from each other. Therefore, we coat them by an insulation layer. These are typically based on polymers in solvents, and we classified them according to their temperature resistance. To coat the wire, we can choose between a painting or a extrusion process. With the painting, we heat up the wire and pull it through the insulation paint. To adjust the layer thickness, we can repeat this process to add additional layers and add the size of the insulation. In the extrusion process, a fillet plastic granulate is first heated up by heating bands, after which an extrusion screw press the melted plastic material out of the die, and simultaneously a copper wire passes through the extruder and is coated with this melted plastic at the die's outlet. The layer thickness is determined by the size of the die's outlet in the extrusion process. Now that we know some basics, we can look at the manufacturing process for hairpin stators. Starting with an overview over the generic process chain of the hairpin technology. Um, the pin itself changes from a straight geometry after the cutting to a U shape before it is inserted in the stator slots. After that, the end gets twisted to align the pin for the welding process. The structure of a hairpin stator consists of a connection terminal, also called busbar, a contact ring, the hairpin basket or plug-in coil, the slot insulation paper, and the laminated stack made of thin metal sheets. Next, we will go through all 15 process steps of the generic process chain in detail that are shown on the right-hand side. Um, we need, first of all, we need to notice that the quality of the flat copper wire is highly relevant for the quality of the process. We get in troubles in the bending or stripping process if the copper core is not correctly aligned within the insulation cover, or the insulation surface is damaged in any way. These errors lead to electrical short circuits and scrapping the whole stator after the electrical testing, which is the last process step. We can avoid these errors in the production line with optical checks of the cross section and checking of surface defects. Alternatively, we can try to source these checks out to the supplier and ask him to mark the defects on the wire. Process step number 1 is straighten the copper wire. When copper wire is wound onto big coils and supplied to the production lane, it gets bent, and that needs fixing. This is done using a multi-step straightening process with special tools to make the wire as straight as possible, like shown in the picture. This is important because it improves the accuracy in later steps like setting and welding the hairpins. The quality is directly bonded with the quality of the wire in terms of damage and contamination, as well as at the consistency of the material parameters, especially the temperature in the production environment. And the quality of this process is influenced by the position of straightening rollers and the speed of the wire feed. Process step number 2 is stripping the copper wire. The aim is to remove the insulation layer from specific sections of the wire, typically the coming ends of the single pins, to expose the bare copper which is needed for electrical connections. Although contacting itself is one of the last steps in the process. The stripping is usually done using mechanical tools like milling or laser tools that precisely strip away the insulation without damaging the copper underneath, like also shown in the picture. It is important to have a high repeat accuracy within this process and to remove the insulation completely, because insulation residues have a particular influence on the welding quality. Process step 3 is to cut the copper wire to length. Cutting copper wire to length involves using precise cutting tools to trim the wire segment to specific length needed for forming the hairpins. This ensures each pin fits perfectly into the stator assembly. We can use multiple tools to cut the wire, like shear cutting, or we use stamping. We always have to keep the wear of the cutting tools in mind to ensure a stable process. And it is important that we cut the wire at the section we stripped before and not damage any insulation. If we talk about eye pins, then the pins are finished now and could be joined to the stator. For the U-pins, the next step is the bending process. So let's take a look on process step 4, bending the copper wire. This involves shaping the cutted wire segments into U-shape hairpins using specialized bending machines, ensuring they fit accurately into the stator slots later. It is important to adhere the specific shape with millimeter precision. The quality is influenced by the forming time, speed, and force, as well as the material parameters. These could change by different aspect ratios of the conductor or different materials of the conductor, like aluminium or copper. Let's see how the bending process looks like in the video, starting with a straight pin, which is formed into a U-shape by CNC bending. This is done by a machine from the supplier Varfios. Okay, let's go to the next step. Or not even the next step. On this slide, we see some alternatives to the CNC bending process we just seen in the video. Comparatively, we pay in this process for the highest flexibility with a high circle time. Much faster are the other three bending processes we see on this slide. The free bending with a gripper that takes the free pin leg and pulls the hairpin apart. We see the die bending that uses a die and a stamp, and the swivel bending, which is kind of a combination of these two. We have all of these four technologies in the market. From my experience, the die bending process is very popular, at least for the 3D bending step. Process step 5 is to insulate the stator slots. This step is to prevent electrical contact between the copper hairpins and the stator core, ensuring a safe and efficient operation. We cut the insulation paper into pieces that match the size and the shape of the stator slots. Then we carefully insert these insulation pieces into each stator slot, ensuring they fully cover the inner surface to prevent any electrical contact with the copper hairpins. A huge quality influence is, of course, the slot geometry, which potentially blocks the paper insertion. Next step is the pre-assembly of the hairpins. There are different ways to arrange and align the bent copper hairpins in preparation for joining them to the stator slots. We divide between rectified screwing in, counter rotating screwing in, radial feeding, and intermediate plug. We have to be aware of the handling forces and keep the hairpin geometry deviation in mind. This process step ensures that each hairpin is correctly orientated and positioned for a smooth integration into the stator stack during the final assembly. After we arrange the hairpin to a basket, we join that hairpin basket to the stator package in process step 7. The hairpin basket are transferred from the pre-assembly station using multiple gripper system and then inserting axially into the stator sheet stack. Finally, the hairpins are aligned in the axial end position, for example by using a pressure plate. At this point of the process chain, it becomes obvious if we had any errors in the forming process of the hairpins. Plastic deformation of the hairpins would not allow us to join the basket without damaging the pins into the stator slots. So it is kind of a natural check, but it would be better if we identify errors previously. Now that the pins are in the stator, we have multiple steps to align the pin ends to each other for the welding process. The first is process step 8, the widening. We can do the widening by a radial or an axial process. In either way, we have to be careful to not damage the surface of the insulated pins. Widening involves a slightly expanding of the hairpin ends to ensure a secure fit and proper alignment with the stator slots. And also this is necessary to preparing them for the next step. And this is process step number 9, twisting the copper ends. Twisting is done by rotating the ends of the hairpin to interlock them securely. To be able to grip the ends, we done the widening step before. The rotation is typically achieved using a machine that grips and twists the hairpin ends together, ensuring they are tightly connected and properly aligned for optimal electrical flow and subsequent welding. This only works if the shape and position tolerances of the copper ends were secured, which shows the high interdependencies with the earlier processed steps. A comparison of an untwisted and a twisted hairpin basket is shown in the picture on this slide. Now, process step number 10 is cutting the copper ends to length. The step involves trimming the protruding ends of the hairpins after inserting and twisting, ensuring they are uniform and ready for welding to form a smooth electrical connection. We can see the initial state as well as the final state in the drawing on top of the slide. This is a process step. We only have to correct inaccuracies of previous steps. In an ideal world, if we would align perfectly through the process steps before, this cutting process could be saved. Again, because this is a cutting process, we have to keep an eye on the wear of the cutting tool. Process step 11 is one of the most critical ones. Contact the copper ends to create a continuous electrical circuit. This is typically done using techniques like laser or resistance welding, which apply heat and pressure to melt and join the copper ends securely, ensuring strong electrical conductivity and mechanical stability. We prepared 2 videos to show you this process in detail. This is in normal speed. And we also have one in slow motion. This video has 5,000 frames per second. The quality of the welding is influenced by the energy input of the laser, the general laser power, and the laser focusing. The feed speed is also important, like the preparation and positioning of the welding process. Like shown on the slides before, we have several process steps to ensure this. This video shows a perfect welding result. After welding of the pin ends, we need to contact the bus bar to be able to connect the stator later to the power electronics. This is done using welding techniques that securely fuse the connections, ensuring efficient electrical flow and integration into the motor's electrical system. This is one of the few process steps which is hard to automation, why we still see workers doing this process step. Once again, the energy input, the laser power, and the focusing are crucial for the quality of this process. The last process step we have a look on in detail is step number 13, insulating the welded and bar copper ends. The technique we see on this slide is named potting. The resin is sprouted over the ends and allowed to cure, creating an insulating barrier that protects against electrical shorts and environmental damage. Quality features of this process are the layer thickness of the resin, the dielectric strength of the insulation, and to avoid air pockets in the insulation during this process. At the end of this chapter, we summarize the process chain step by step. Step 1 is straightening the copper wire to remove the bend of the coil. Step 2 is stripping the wire to remove the insulation layer at the future pin ends. Step 3 is cutting the wire to the pin length. Step 4 is bending the copper wire into its U shape. Step 5 is to insulate the stator slots with the insulation paper. Step 6 is the pre-assembly of the hairpin basket. Step 7 is joining the hairpin basket into the stator stack. After rewinding the copper ends in step 8, step number 9 is called twisting to align the pins for the welding process. In step 10, we cut the pin ends to an equal length. And finally, in step 11, we weld the ends to a continuous electrical circuit. In step number 12, we add the bus bar to the stator, and in step 13, we insulate the copper ends by potting. After that, we insulate the stator with a resin in a trickling process. The last step, number 15, is the electrical testing of the stator to ensure the functionality. That was the manufacturing process for the hairpin stator production. Now we take a short look on the market and patent situation before we look on the product and process restrictions. We definitely see applications of all three technologies in today's market. The continuous hairpin is today more of a marginal phenomenon. The only full electric car that I know is the Lucid Air, a luxury car with one of the highest range in the market. So this technology offers a lot of potential for the future in other applications. We see less iPin applications, like we see today in the Renault Scenic. And we see that the number of electric cars with U-Pin, like the Volkswagen ID.3, is increasing. Although we still have many cars with round wire stators in the market, like the old Tesla models, we see that the new Model 3 and Model Y are switching to the U-Pin technology as well as the rest of the market. In our perspective, until 2035, this technology will be dominant in electric motor applications for automotive. On this slide, we see some examples of the variety of hairpin stators. Hairpin stators differ in terms of their active length, their diameter, their number of slots and number of pins or conductor in this slot. They differ in the height of their connection or bending side, and they differ in their winding scheme, or among other things. And each product variant requires an individual adapted process chain. Today we took a look on the generic process chain. This slide shows a lot of average numbers for stators in the current market, but I think the most interesting is the cut view on the left of the Nissan Ariya and the BMW iX1, where we can see the difference between a slot with round and ones with flat wires. We see significant differences in the winding design and the number of wires per slot. In the picture, we see 4 flat wires per slot for the BMW, but there are designs with up to 8 or 10 pins per slot as well, which makes the production and the cooling principles for this stator even more complex. Due to this complexity, there is still much room for innovations or differentiation in the process chain. Most likely, we see some improvement in the critical process steps, and the number of patents prove this. We see the highest number of patents for the bending, twisting, and welding process, which shows us that there is much to improve until today. In Chapter 4, we take a closer look to the product and process restrictions. We see some product restrictions with the hairpin technology. For example, the length of the hairpin legs can cause restrictions such as difficulty in fitting into the stator slots if they are too long or too short. We see potential misalignment during the assembly, and we see challenges in ensuring the consistent electrical connections and mechanical stability across all hairpins. We want to achieve a high slot fill factor with this technology, but a high slot fill factor can lead to restrictions like increased difficulty in inserting hairpins, potential overheating due to limited cooling space, and challenges in ensuring uniform insulations and electrical performance. We also see some troubles with the skin effect, which is a phenomenon where at high frequencies, electric current tends to flow more on the surface of a conductor rather than through its entire cross-section. This reduced the effective area available for current flow, increasing resistance and potentially causing inefficiencies in electrical systems. By the way, that's the reason why we don't use a single flat conductor which fills the whole slot. We also see restrictions in the effects of the slot shape, and also in the number of windings per phase. We already learned that the process steps in the hairpin stator production are highly interdependent. A good example is the welding process. That's the point where errors in earlier process steps become obvious. So the error in the welding process itself does not necessarily result out of a bad welding. First, we see that the welding of two hairpin ends may not possible due to the bad alignment in the twisting process. Second, we see that the insufficient stripping of the insulation layer can influence the welding results. And third, we see that bad cutting results in weld splatter that can damage the insulation of other hairpins in the same stator. Another example would be an insufficient straightening that causes geometric deviations in the shaped U-pins, which then could result in a collision when we try to join the hairpin basket to the stator stack. To remedy this and ensure continuous production, tests and buffers are installed between the process steps. On this slide, we see such testing positions in the production chain of hairpin stators. The first test, laser measurement, could be placed between process step 1, straightening, and process step 2, stripping the copper wire. Right after the stripping, we can have an RFU analysis. Test number 3 could be after the bending, a geometric measurement. And after process step 7, joining the hairpins, we can have a visual basket control. Another visual testing could be after we cut the copper ends and twisted them. And test number 6 could be a visual weld seam inspection after we contact the copper ends via welding. Test number 7 is typically a cradle or e-test, like test number 8 at the end of the line. The only reason we do this before the impregnation is that when we see a failure or an error in test number 7, we don't have to bring the stator to the highly investing impregnation process. Let's finish with an outlook and a summary. In this presentation, the hairpin technology as an established winding technology for automotive traction drive was discussed. In this presentation, characteristic product properties and the process chain of different plug-in coil concepts for hairpin stators were presented. In this presentation, you got familiarized with the production process for hairpin stators, including quality determining features. So, thank you for your attention. I look forward to welcome you to the next module, rotor production. See you.